Hi everyone, welcome to another video from the Sustainable Computing and Optimization Training Resources. My name is Preston Abity, and today's topic of the video is going to be over artificial neural network basics. Now, the first question is, why would we use a neural network? Well, if we imagine that we have a large system with a bunch of measurements coming out of it, for example, such as a data center or a building, and you can see in the bottom left here, if you'll recall from our previous video, this is an example model of a data center, and you can recall that we have lots of input and output data. There's a lot going on inside the system. It's very complex. And so we don't necessarily have a model that comes to us through, for example, physics-based modeling. But of course, to do any kind of work on it as an engineer, for example, controls or analysis, we need to know this F that we can see in this, for example, nonlinear ODE here. So that way we can do some system analysis, of course. And so to do that, we need a model. We need to find that F. Now, first, though, the difference between what we're used to, which is continuous time, and the real world, where we use measured information, which is what we call discrete measurements, is that the modeling changes up a little bit. Now, as we saw in the dynamic modeling video, a typical way to model a continuous function is with this nonlinear continuous ODE. And as just a reminder, this is the continuous definition of a derivative as well, where you have that limit of h approaching 0. Now, in the real world, we unfortunately can't take measurements at every instant in time, where in this continuous model, t can be any value in time. And so since we have that restriction of our real sensors and kind of their refresh rate, what we end up with is, instead of t being able to be any value and this h approaching 0, is we find that h is typically a fixed value, and it's based on that sensor update rate. And typically, we'll swap out the h in that definition of the derivative for a delta t, or that time step between measurements that we're receiving. Now, to follow that, of course, this is just a notation thing. Time, because it's in fixed intervals of delta t, we typically will regard time in the discrete model as a k, which is how many of these fixed intervals delta t have passed. And so you can see the reformatted definition of the derivative here with the k and the delta t. And so what we get then for a discrete model is something not too different from the continuous model, but you can see that we have now a discrete ODE here at the bottom, which represents the system, but as it's seen through discrete measurements. Now, of course, an ODE is just one way to model a system in general, and so if you'll recall from the dynamic modeling video, we also have, for example, state space models. And so that can be discretized as well. In fact, it would look something like this here if you were to discretize a different type of model, where here for the state space you have your states, your inputs, and then that time step k, as I've explained. And so now we have a model form that is able to accept discrete pieces of data. And so we want to know now, can we get that F, or in this case FD for discretized, can we get that using a neural network? Well, first, what is a neural network? Well, if we were to take a look at, firstly, what information is going into this system, we have here, and this is just for again a nomenclature thing. What we're looking at specifically is called a recurrent artificial neural network. The recurrent means that we have past information being fed back into the system. And so for this system, the information that we have that we can input into it is, if we imagine our system is at time step k, that's our current time step, we have the following information available to us to feed into the system. Now, Of course, this looks reasonable because I've only written out 4 values here, but if k becomes large, this of course becomes quite a lot of information, and we can kind of intuit that we don't necessarily need all of that information back to the very beginning of our system operation. And so what we'll do is we'll select a subset of that data shown here so that we can kind of not burden our computation. And so what we'll call these sets of input and output data that we've sectioned off from all of our past information is we'll call them our delays. And these delays will get fed into our artificial neural network like so, where we have our plant is the network, and that information gets fed into the network to produce the current output value y of k. Now, if we were to zoom in on this plant, right, this artificial neural network, to see what's going on, we would find that we've got 3 distinct sections of our network. The first of these is the input layer, where our delays go. We have hidden layers, which is where our data gets processed. And then we have finally our output layer, which calculates the outputs of the system by combining the processed data. If we take these kind of covers off, what we'll find then is that we have in the layers these distinct sets of neurons, which represent either data or processing of the data. Now, the first section of this is our input, which is in this case our delays, as I mentioned before, so previous inputs and outputs. Next is the hidden neurons, and these process data, which I'll explain in a little bit how they do that. But here in this case, I've considered that we have NH of these what are called hidden neurons, and they're called neurons because, as a kind of to allude to the neural network and how these are supposed to mirror the processing that goes on in our brains. And finally is the, in this case, just one output neuron, but it could be multiple depending on your system. But we have our output, which takes all of the processed data from the hidden neurons, and it combines all of it to produce a single output at time step k. And so, of course, this is fine and dandy, but this is just a picture that I've shown. And so how does this neural network process the information that we give it? Well, if we take a look at the first hidden neuron, we'll find that each line represents data flowing from one neuron to another. And this processing, so to speak, is a weight, as you can see, multiplied by each of the data points being sent into this neuron. Now, at the end, before it gets into the neuron, all of this information is summed together, sometimes with a bias at the end, and then it's processed in an activation function, phi, as you can see on the outside of all of this. Now, this phi can be a transformation like a linear or a quadratic, but it could also be complex transformations or processing, like a tanh function or a ReLU function. But at the end of the day, once it's processed, once that information gets to the neuron, gets sent through phi, we have this A1, which is our neuron activation. And it can be thought of as like the state of the neuron at time k. Similarly, if we were to look at this last hidden neuron, NH, we would find that we have a similar process for all of these hidden neurons, where we then have the activation at time k for that final hidden neuron. Now, of course, here I've only shown one hidden layer, but we could imagine that if we were to have multiple, the only difference would be that these inputs, so these U's and Y's, would just be the data from the previous hidden layer as opposed to from the input layer. And so with that, though, now once all of our hidden neurons have processed the data, this data will then get passed to our output neuron, or neurons, depending on our system. And so with this, we have a similar thing where we sum all of them together. They have a weight corresponding to them, as well as a bias, if you'd like. And then finally, one more function, this f on the outside of everything, to calculate y of k. Now, a common choice for this final output processing is linear, and so typically it'll be different from the previous activation fees, which is why I've chosen to remark it as f, but again, it can be tailored to your needs. Now, if you'll notice, we have now the same kind of form as that discrete nonlinear ODE that we saw earlier, the one that we were hoping to get and be able to find the f, as I was calling it, in order to calculate that y of k. And you'll see here that we have, of course, f, but we choose f, we know what f is. We have this very similar expression where we've got some nonlinear processing and all of our past measurements. And so it looks like we're on the right track. It looks like a neural network is going to give us this kind of expression that we're looking for to model our complex system. Now, of course, though, that's fine and dandy, but it doesn't mean much if we don't have these parameters, because that's the real known of this problem, is we have to know these weights and these biases. And so how do we go about doing that? Well, if we take a look here, when we are teaching, as we can call it, an artificial neural network, what we do is we typically will take some existing data. So we have however much information of past measurements that we've taken, and we'll feed it to our neural network to teach it those weights and biases. And the way it does that is it goes through 3 stages, where the first is the training. And now this consists of optimization, where it uses 70% of the data that we give it in order to optimize and determine how to get a best fit, or the best weights and biases rather, to get the best fit. And it does that through several loss gradient propagation methods, but I won't get into that too much. There are just several options that we have when choosing that. Once it does that training, though, and it gets those weights and biases that it thinks are good for the data it has, it sends it then to the validation stage, where it uses some more of the data that the system hasn't seen yet, and it sees how the parameters perform on that new data. If the net doesn't perform well, of course, though, with the new data, then it'll go back to training, and it'll try to figure out and re-optimize in order to get some new weights and biases that will be sufficient until it meets those criteria. And then, of course, once it meets those criteria, it moves on to testing, where the final parameters that come out of validation will be used on the final pieces of data that haven't been used, and the final performance of the neural net will be determined. Now, this is great. We have a way to determine our weights and biases. And if we take a look at this kind of visual representation of the system, then what we find is that we've got that optimization process, that kind of loop to make sure that the weights and biases are appropriate. And once we get those weights and biases, we move to testing. And once we have that, we now have a way to represent this large, complex system and do our regular controls engineering on it. So, for example, that data center now, we can parameterize it with our with these weights and biases, and then we can model the system just like we want. So artificial neural networks, they provide a path for modeling that is now based on data as opposed to things like physics. And so I hope that this was helpful in increasing your understanding of them. I'd also like to mention that this work is supported by the National Science Foundation, and please feel free to check out any more videos in the Training Resources playlist.